Welcome back, everybody. I feel shiny. Good. All right. So these are the 4 from yesterday. The last one, and you do not have to jot this down right now, but there is an alternative. If we look at this one last time, and I'm going to put way less thought and time into this. Let's say I have the same rough thing, and we'll just roughly split it up here. I'll do 4. Rectangles are pretty cool, right? That's a little play on words there, but not that great. Are there better shapes than rectangles to estimate this area? Like we saw, there's an issue with rectangle. If I do this one, it's too low. If I do this one, it's too big. If I do the one in the middle, maybe it's about right, but there's no like true guaranteed Goldilocks here. Do we agree? But this is increasing, right? What if I do this? I no longer have a rectangle to find the area of, but a what? A trapezoid. Could we do a trapezoid here also and get a pretty good trapezoid? And another one here, and that one's going to be more rectangular, but it's a little trapezoidal. Could we do this with trapezoids instead? Do we get more or less air if we do it with trapezoids? Not air like, but error. Less, I think. So maybe there is a way to do it with trapezoids instead, which would be convenient for us. So today, as we're looking at stuff, we get to revisit some of these summation things. Do you guys remember, who's the story about? Carl Gauss. I'm sure I told you the story last year. I'm certain of it. And for those of you that I had last year, sorry, because you're going to get the same thing, because I think it's really cool when we work this out for the first time together. Carl Gauss was the super annoying 8-year-old in class in the 1800s who was just bugging his teacher. And the teacher said, all right, Carl, shut up. I want you to add these numbers. Add the first 100 digits. And no calculators existed or anything, so he had to add them all up. Do y'all remember the story? Okay. So that's the story, I guess. But let's jump in. Let's get up to talking about old Gauss. So here we are. Today, rectangles work pretty well, right? But yesterday we used 10 as the most for there. What's better than 10 rectangles? Infinitely many. Like 11 was also correct, just so you know. But infinitely many is the best. So we're going to really get a solid definition. We're still in 5.1. So if we want it, we can call this 5.1.2 technically, or 3, I'm not sure. But we're just going to give ourselves a nice formal definition. We're going to say area under curve and under a curve. Can I just say under curve? I'm going to. From A to B. Now, this is exactly what we've been doing. The area under the graph of a curve between the function and the x-axis from x equals a to x equals b. We're just using like 30 less words. So here we go. If, and big ideas coming out here, if a function is non-negative, which remember we say that to include if it's 0, it's okay. If a function is non-negative on the interval for x, the closed interval a to b, then we can partition, and I know that this is going to be wordy for a second, but I promise it'll all be math here soon. We can partition the interval, and we're going to pause there while I let you guys catch up. If a function is non-negative for x in some closed interval a to b, then we can partition the interval. And right here immediately, which interval are we partitioning? A to b. We can partition this interval from a to b into n subintervals. And a lot of this is repeat, but if I'm repeating stuff, it's not because I'm old enough that I'm just telling you the same stuff over and over. It's that I'm really stressing the importance of what we're doing. We can partition this into n subintervals with width. And how did we find the width of any subinterval yesterday? Good. Delta x equals, whoever quietly whispered it, you were spot on, b minus a over n. And we're going to put a period there. So there's nothing new here. If you give me an interval where a function's above the axis, I can cut it into however many pieces by doing this. Okay, awesome. In any interval, and I'm going to say in each interval, there exists, which is there a symbol for that? For there exists? Okay. It's a backward capital E if you want to use it. There exists a rectangle whose area is, gosh, how do we find the area of a rectangle if we're talking about this function f? Maybe some ugly subscripts or something. We might have seen it yesterday. Ooh, you're close. C1 is included in it. If I want to know how tall my rectangle is at some value, I need to plug it in where? So if I want to figure out, ooh, say it again. Oh, I thought it was Fern, but it might not have been. What did you say, Sean? Or Rafa? I don't know. It was over here. F. There we go. F of C sub I. This is the what of the rectangle? The height. What if I want the area? What do I have to multiply the height by? Delta x. Good. And that's our width. I'm going to say wide so it fits. Okay. This every time will happen. Now, we have n rectangles at this point because we're using n partitions. Okay. Anything here that I've lost you with? Now, we'll look at these specific things. I'm going to make a little note here, or in parentheses, and I'll even change color so it stands out as its own little thing. I elected to write lowercase c sub I. Does it indicate anything? Is it lower sums or left sums? Lower, good. So for this, you're right that they are lower. If it's not specified what we do, though, I don't want us to have to think lower or upper, because with enough rectangles, it won't matter which one we use. Do you think it's easier to use the left point or the right point? The very first point of the interval or the first point in? Can we agree that it's easier to pick the first point rather than trying to shift it? We'll just go default to left point. To left point. And we'll see why this doesn't really matter whether we pick the lower, the upper, the right, the left. We could do it with any of them. Okay, we'll default to the left point where we get that lovely expression from yesterday. Now, all of this is coming together today, so nothing new still, I don't think. Is that true? Does this all feel like the stuff we discussed yesterday and the day before still? Okay, good. So when we do this, we get a bunch of little rectangles. Now, yesterday we said we can write S sub n, and it is the sum from I equals 1 to n of this thing, f of c sub I times delta x. And this specific expression right here is the area when we add up all of them, right? This is the sum, and we'll put this, of how many rectangles? Good, love it. Abigail said n, so I agree with that. The sum of n rectangles. Again, nothing new, but we're about to pull the calc back into this. Did this, when we did it with some number of rectangles, did it give us a perfect area? Not quite, right? We still had little unders and overs, and even with 100,000 rectangles, we're still going to have a little bit of variation. You guys have already answered this. What's the best number of rectangles? That's a terrible way to ask a question. How many rectangles should we use if we want it perfect? Infinitely numbered. If you didn't catch that, infinity is not a number, is why I changed the language there. It's a weird semantic thing. Okay, so here we go. This is the sum of n rectangles, but we want a lot, or infinitely many rectangles. So here we go. The true area. I'm just going to call it the area, is exactly found with, and here's the big moment. Can I get a really not very enthusiastic drum roll? Yeah. All right, cool. Check it out. Good. I can feel this electric air. Love it. Area A. Well, how do I let something go to infinity? Like, if I want to know what a function is doing at the end of its like intervals all the way out and about, I say the something as n goes to infinity. It was a huge focus for the entire first 4 chapters. The limit. We let it go to infinity. So let's do it. The limit as n, which what does n represent again? What about the rectangles? Not just rectangles, but the number of rectangles. And that's probably what you meant, and that's good. But we take the limit as n approaches infinity of s sub n, which do not let the notation freak you out, Aisha, okay? Because I can tell you're already stressing about what we're about to do. It's okay. This is the same thing as the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x. Okay. It looks gross. I get it. It's not near as bad as you think it's going to be, I assure you. But all this is saying is, let's let the number of rectangles go to infinity and see what it equals. That's it. So this is how we're going to get to work through this. This is easily, you know what? It's so important that it doesn't need just like highlighted there. Are we feeling grass important or star important? Well, smudge isn't very cool. So we'll do grass and we'll just go crazy. This is so important that we're going to plant it and let these seeds grow. A little botany pun. All right. I still don't see purple. I see pink. You guys see purple? Pinkle, deal. All right. So here, one year I took the time to write "You're all nerds," and then I copied it and made it the dab image so that when I did this, it just said a bunch of "You are nerds" when I did it, which it's coming back because Abigail apparently would get a kick out of it. Okay, so here we go. If we're gonna do a bunch of sums, then we need some rules. Not using the, see, so that's grass if you can't tell, and you can't tell, but I can write with it like this, and just to show you, this is what I did before, and everything that I do is only because I find it funny. Can't see it still, but let's keep going. Whoa, let's keep going, and we'll go back to grassland. I can't even tell here. They're all little grasses. And if you do it right, they're all little, you guys are nerds, or whatever the case might be. But we'll go back out to that. All right. So, too far. Okay. Do we want to, okay. We're going to recenter here. Do we want to see where these rules come from? And maybe like prove them that they work for k, and if it works for k, then it must work for k plus 1, and do a big inductive proof? That sounds like enthusiastic yes. Do you guys remember doing proofs by induction last year? Show it works for 1. Assume it works for k. Show that if it works for k, then it must work for k plus 1. And if it works for k plus 1, it must work for k plus 2. And we do that forever. Anybody really wanting to do inductive proofs today? Okay, here's the deal. I'm going to give you some formulas. And there's some times in here that I don't really love just saying, here's the formula. If you have any interest or would like to see it again, because I know that most of us have done it, and you want to come and write an inductive proof with me, can't threaten me with a good time. Like, yeah, come in at lunch. We'll do it. I'm good with that. Okay, here we go. If we're not going to do our proofs and all that good stuff, I'm okay with it. Let's get some rules. And just to be really clear, I mean, let's get some summation rules, which I think is nicely stated like this. What was that? All right, Rafa's animated. So check it out. For this, we're going to meet in the middle. And I'm going to use bullet points here. I don't normally inside, but I don't want to use a dash or a tilde that could be misconstrued as a negative. So check it out. Our first one is our constant rule. And we'll do a little bit of expansion. I'm going to do it in pink up here so that if you need it, because you've never seen summations or you don't remember how to do them, we have it. But all you really need is what's written in black. If I want to take the sum from I equals 1 to n of some number, and I'll just call it C for now. For this, in pink, you do not have to write. Where does this, how do I want to phrase this? Does this have an I in it right now? Like down here, there's certainly, I start at the index I equals 1, but does the argument of my sum actually have an I in it? So when I start at I equals 1, what does it spit out at me? C, and this is the I equals 1 case. And then we just keep jumping. Plus, what's the next one? When I make I now equal to 2 and I plug it in for the I that's not here, what does it give me? C, and that is going to be when I equals 2. And this is going to keep going until I get to what's the last one? The sum or the summation from I equals 1 to where? So this is the nth choice. How many C's are in this? There's n of them. So if only there was a more convenient way for me to write C plus C plus C plus C if I know that it shows up n times. C times n. That easy. Or nc if you would rather. But it's just Cn, just that constant times whatever n was. Okay. In pink is purely optional, right? So we need this rule. Like, I'm going to be honest, for the next several nights, you probably want to write these on top of your assignment or get ready to turn your notebook pages over and over. Okay, we get constants. And then we get Gauss's idea, which is our linear sum. And our linear sums are of the form, the sum from I equals 1 to n of just something nicer. Now, I could use whatever letter. I use I as the index here, but let's just say it's I. Just itself. So same thing. If it's in pink, it's just me writing it out, and it's purely optional, but I need you to pay attention whether you write it or not. What's the first thing going to give me when I plug in a 1? Plus, what's the next one going to give me? Plus, all the way until I get to where? N. Does anybody remember 8-year-old Gauss's brilliance here? I said we weren't going to do this, but we're going to do it because I think that this is awesome. And I hope that it's a real true story rather than just a legend. But this was a problem that Gauss's 3rd grade teacher roughly gave him and said, quit annoying me, spend your time doing this. Because if I said add up 1 plus 2 plus 3 plus 4, and I said no calculator, just do it by pen and paper, how long would it take you? Like, estimate, what do you think? I think with 10 minutes, I could get it. I'm pretty confident that 10 minutes would be enough time for me. Would 10 minutes be enough time for a 9-year-old? Probably not, unless your name is Carl Friedrich Gauss. Because Gauss did this, and he said, oh, and he might not have had this exact notation, but he might have. I don't know for sure. He wanted her to add up, or she wanted him rather, to add up the first 100 numbers. Everything here is just to make sure that we can appreciate how cool Gauss was. So he thought the following. Oh, I'm adding up the first 100 numbers like this. And then he thought it out. He said, oh, that's 1 plus 2 plus all the way up to 100. Do we agree that that's what he's doing? Now, again, I don't know if he had this notation. And then he thought, you know what? I'm feeling Gauss-tacular today. I'm going to add this to itself. But he had a brilliant thought. And instead, he said, wait a second. If it's 1 plus 2 plus 3 all the way up to 100, I could think of it as 100 plus 99 plus ... all the way down to 1. And I still add up all the same stuff, right? And then he had this brilliant idea. When he recognized this, he said, hey, wait a second. And I'm going to cheat with my notation just so you know. This is just 2 times the sum on the left side. And then let's see what happens here. 1 plus 100 was 101. And 2 plus 99 was 101. And all the way down the list, we end up with 100 plus 1, which was 101. And Gauss said, okay, well, here's my sum. That's all fine and dandy. I don't want it to be times 2. So what should he do with it? If he wants just the sum, he divides each side by 2. Now, we're going to take one little short trip through here. How many of these do we have? So what Gauss recognized was it was just 101, and there's 100 copies of it. And all of a sudden, this is a much easier problem to do. What's 101 times 100? Just add 2 zeros to 101 and you'll have it. 10,100 and divide 10,100 by 2. And all of a sudden, Gauss at 8 or 9 years old came back to his teacher like 2 minutes later, and this is what he had done. I was not that bright. I don't know that I'm that bright now still, but it's awesome that it worked out. With that in mind, with what Gauss did, what's the rule? That's n, right? Okay, so there's an n. And then what's this with relation to n? N plus 1. And then it all got divided by 2. Here is the rule if it's just a linear. Okay, we are not going to Gauss out these next few, but I'm just going to give them to you. We're only going to go through cubics here. We'll double check, but I'm pretty sure your book goes up through the quintic, which is 5th power. So if we had linear, we better knock out quadratics. So let's say we take the sum from I equals 1 to n of what needs to be here, I squared. Do you guys still want the pink parts here? Okay. I think I just saw an affirmative. That equals, what's 1 squared? 1 plus, what's the next number going to be? 4 plus 9 plus all the way up to n squared, right? Okay. These ones, I wish I had a good way to tell you like to memorize these. I think we'll do enough problems that you'll get a few of them memorized, but I am being 100% sincere. I would have this available while you're working homework for the next few days. Okay. It turns out this one is equally nice-ish. It's a fraction. We get n times n plus 1 times 2n plus 1, all divided by 6. And the cool part that if you guys save your notes, how many of you guys still have your notes from pre-calc? Okay, anybody like burn them at the end of the year and everything's done and you're just tired of it? Fair. If you look back through your pre-calc stuff, specifically to chapter 7, I guarantee you find the proofs of all of these. We proved every single one of these last year. I'm sure of it. Okay, one more that we'll do together, and then I will point you in the direction of either we'll find it in the book where it would be. What needs to go here if we're doing cubics? I cubed. Now, I'm not going to write this one out, but this is 1 plus 8 plus 27 plus 64. They're just the cubes. Turns out this one gets brackets. We have n times n plus 1 all over 2. And my brackets were simply there so I could square it. Okay, you may see this one presented differently, just to make sure it's there. If you would rather use this variation, I'm okay with it. They're the same. Okay, so in your text, anybody following along in the book today? No, that's okay. So in your text, and let's find the page number real quick, just so that you have it. You will find, and I think that there's some more of these listed, but let me verify that. Oh, maybe they don't give it to us. Why would they not? Oh, nope, they're in here. If you look at page 388 is where it starts, and they're just little purple boxes on the side that says, recall this. We have on the left, recall I, or the sum of linear, and then on the right page, we have the constant and the square. But I do also see that if you go to section P8, which I'm looking on page 388 right now, the left purple boxes, one of them says, hey, do you need more work with this? Go to page P8, which is actually pages 72 and 73. So I'll open up my textbook to pages 72 and 73 real quick, just to verify. And they do not go any higher than cube. So disregard everything that I just said. Psych. All right, scratch that. If we need fourth or fifth, I'll find them and I'll get them for us, just so you know. All right, should we use these and do some big problems? Good. Awesome. All right, so let's jump in. As we're looking at these, are these somewhere on a page that you're going to be able to reference? When we work an example, are you still going to be able to see them? Good. You need to. Okay, unfortunately, this screen must die. All right, so let's knock it out. We're going to do these, and we're going to use left points or right points. We'll decide. Earlier, we thought that maybe left points seem easier, and that's what we wrote. If we go back and change it because we realize that left points really aren't nice, that's okay. Like, it doesn't matter in the end. So here we go. We're going to jump right in. Example. I want us to find the area. Now, remember, the real directions will say between the graph of this function and the x-axis. I'm just going to say under. Under, we'll do a nice one. F of x equals 3x. We'll start chill here. For x is in the interval, the closed interval from 0 to 10. Now, the cool thing about this problem is we're going to do it the super calc way. And then when we look at it, we'll see that it's really, truly just a trapezoid or a triangle. And we can check the area nicely. But let's do the calcy way, and then we'll verify. So we have some work to do. And we're going to do left and right points. Which one do you, we'll probably do both of them together. Where do you want to start, left or right? Okay, so for A, we'll say using left endpoints. Okay, so we do not have to physically graph this, but it might help when we need the graph. I'll sketch it, and you guys could also sketch it, but we're going to wait to sketch it until the end. Okay, using the left endpoints. If I want to find the area, I know it's going to be the limit of a sum, which is kind of ugly, but there's some stuff that we need. We need to know what we're taking the sum of. So f of c sub I and delta x. Do we have a way to find delta x? So let me rephrase rather than do we have a way, because that's just yes or no. How do we find delta x? B minus a over n. Now, did I tell us how many rectangles we're using? So if I didn't specify using 5 or 10 or 20, how many do you think we're going to use? Infinitely many. So we can't plug in n right now. I can't plug in infinity. We'll let that happen in the limit. What's b? Minus a all over n. We just keep it n, which I think we can probably all agree it's just 10 over n. Everybody okay with that? Now, if n was 10 rectangles, each rectangle has a width of 1 at this point. If it's 100, each one has a width of 1/10, and so forth and so on. Okay, so we have that there. Here's where we get ugly, and we may make a change to the comment above. If we think about the number line, and we don't have to draw it necessarily, but I do want us to think about it. I'm running from 0 to 10, right? This is the part of the x-axis that we're focusing on. And I can't really accurately place where these subintervals are because I don't know how to do that with infinitely small. But here's what I do want to think about. If arbitrarily I just say, here's my first subinterval, how on earth, since we're using the left endpoints, where should we start? Is it 0 or is it 0 plus delta x? So we're going to say our left endpoints then, and I'm okay with that. Left endpoints are at, and we got to do a little thinking here. I know that the first left endpoint is where? Now, we're not going to write these out every time like this, but we're just building intuition. The first one's at 0. Where's the next one? And this is a pretty deep question that it's easier than you think, but I'm not just going to answer it for you. If we have what we have written on the board with delta x and our first endpoint. Excuse me. Find me the second endpoint. How do we talk about it? Where is it? And I'll give you guys a moment. We'll clear it up here. If this is my delta x, and we've already decided that's 10 over n, then logically it makes sense that this next point would be at 0 plus 10 over n, right? And the next one after that would be this plus 10 over n again, and so forth and so on. Now, we need a way to be able to generalize this. And the way that we're going to say that is pretty much with this. For the ith subinterval, can I just say sub? I lied. I'll call it subint for my shorthand. Can we all agree subint is short for subinterval? Cool, because we're going to have to write that like a billion times. For the ith subinterval, every left point, and I guess this is for every subinterval, so this feels weird when we write it, is, and forget the grammar part of it, I think we can always just simply take a, wherever we start, plus delta x I times. Now, we are using left or right endpoints. We're using left, so let's think this out. Where's I going to start? When we do our summation, it's a sum from I equals, do we start at 0? We usually start at 1, right? But if my index needs to kick back 1, instead of just saying delta x times I need to kick back 1, don't I? So now I have a way to do it in general. For the first subinterval, when I plug into this, let's just see what we get. For the very first one, we already know it should be 0, and the second one should be 10 over n. And we're just doing this almost inductive check to make sure. Let's verify that it works for the first and the second, and then we're probably safe to assume it keeps working. So let's just check this to make sure it works. What is A on our problem? 0 plus delta x was 10 over n, and we're claiming this is times I minus 1, right? So let's just see if this works, and we should get these points that we already know by taking our steps. If I start at 1, what does this spit out? So if we claim that this is c sub I, and I should have had that there and here as well, terribly sorry. If I plug in a 1, it's 0 plus 10 over n times 0, which is 0. Is that where we should be? And what if we plug in our next interval at 2? I get 0 plus 10 over n times 1, and it says now the second endpoint's at 10 over n. Is that where it should be? Mickey, did I lose you on that one? Okay. So right now, when we get to the point, because I'm thinking ahead a little bit, do you agree that, or can you at least accept that we're going to have to do the sum? Like, and what I'm seeing, and I'll just write it down. I don't want you guys to write this yet, but when we write the sum, it starts with I equals what? And it goes to n, right? Now, if I know that I want this to be my first point, if I were to just do 0 plus 10 over n times I, then when I plug in 1, because that's where we start, it would take me to this point, because it would be 0 plus 10 over n. But I don't want it to moving to the next point, so I can't just plug in I have to kick back 1, so that when I plug this in, it gives me my 1 less. Does it really make sense? Because it didn't feel good when I explained it. It did, though? Okay. All right. So now we have a nice way to say this is what every left endpoint looks like. Every left point. Okay. Do we need to stand up and do some jumping jacks real quick or something? Because I can feel it's getting pretty dry, but the big conclusion's coming. I can tell you're on the edge of your seats. Okay, here's your job. You need to physically stand up, talk to one of your classmates that you haven't spoke with today, and give them a realistic, meaningful compliment. You can also do it to your teacher, just throwing it out there. Compliment one another, real ones, not, hey, you're cool. Like, we're not doing yearbook side signatures for people that we kind of know. We're giving like real compliments. Anyway, every single left point we just discovered has this. Now, we get a decision to make. Do we want to keep it like this, or do we want to distribute? Okay, we'll keep it for now. If we change our mind, we'll just distribute in a minute. Okay, we now know the width of every rectangle. It's 10 over n. We know the height of every rectangle if you give me the I value, and it's calculated by this. All we have to do now is just add up infinitely many pieces. So let's do that. Let's add up all infinity of these. And we'll get there. What's awesome about this is we actually don't have to add up every infinity of them quite yet. We'll get there. Last little thing, since we've done this, we have delta x and I have c sub I, but does that really truly give me the height? How do I actually get the height? If I can identify where my endpoint is, I have to plug it in somewhere. So let's do that. This is the last big part. We have delta x. Let's get our f of c sub I. And when we do future examples, we'll clean this up because there's a lot of stuff going on in this one. Well, let's figure out what f of c sub I is. A moment ago, we just said what c sub I was. This is the same thing as me doing f of what? What did we say c sub I was? This ugly thing, right? Do I really need to include the 0? No, but we're back to that question I asked a moment ago. You guys said we shouldn't distribute. Do you really want to plug it in without distributing, or should we just distribute and bite the bullet here? Let's just distribute while we're at it. Everybody agree that this is 10I over n minus 10 over n. Everybody cool with that? I don't think I made a mistake. That feels right. 10I over n minus, yep, we're good. Okay. I want you now, using the function that we have, to find this for me. What's the function we're actually working with? 3x, but it's not 3x, it's 3 times 10I over n minus 10 over n. And I'll give you guys a second. Once you get it, I just need to know what f of c sub I cleans up to in its nicest possible form. We'll make that a nicer I. Do we all agree it's that? Like there's nothing really to it? Okay. Okay. So for this, again, way more than we really need, I'm going to highlight right now, out of everything that we've done a lot of talking, a lot of extra work just to make sure, I hope that you guys understand where stuff is coming from. Is there anything that we did here that you're not quite sure of, and now 10 minutes later you want to ask? I say that like I'm scaring you away from asking, but please, even if you had a question 10 minutes ago, now's the right time to ask it still. For the most part, feels okay. It's kind of gross for now. What I want to highlight out of all of this, when we start actually doing these problems, like we won't write all this in black, I'm going to highlight what we've, just a summary of what we found and what we really truly need out of all this. In black, if we're doing this problem by ourselves, I would only have this. But I have delta x is 10 over n. Then I would do the work to work out c sub I is this 0 plus 10 over n. And I'm going to write it as 10 over ni minus 10 over n, which is what we just distributed to anyway. And the only other thing that I need, and I don't really truly need to have this written here, but we have to calculate it, is we also need to know that f of this thing is this, 30I over n minus 30 over n. This is the important info that we got out of that. Everything else that we did was just to build the intuition and understand where this stuff really comes from. When we want the actual area, it's the limit as n approaches infinity of the sum, right? Okay, we're going to do the sum first, and then we'll do the limit after we have the sum worked out. And it's going to work really nicely, and we have 6 minutes. We will finish this problem, no doubt. Okay, so let's start setting this thing up. I know that the actual area is going to be the limit of the sum. I'm only going to work out the sum first. We'll do the limit at the end. And we are going to work out the sum first. So let's work this out. This is the sum from I equals 1 to n of, and I'll write it more general first since we've already had this, f of c sub I delta x. That's what we've been working with all day long. Do I know what f of c sub I is? And do I know what delta x is? I'm going to give you a 10-second head start. I want you to plug in what we know, and let's see that we agree on what we've written. Okay, so when we do this, I think we have the sum from I equals 1 to n of what? Okay, so 30i over n minus 30 over n times 10 over n. And then just again in pink, just to really stress this, what is this? For every left endpoint, and this is delta x. Does this give me a bunch of areas of rectangles? How many rectangles? Louder, Sean? Not yet. We'll get there. What was yours, Fern? N right now, and then we'll take the limit after the fact to let it go to infinity. So we have this, and I don't know that we've used this specific language in here. I'm going to work this way just so we can keep seeing it. Well, I have the choice here to do some pretty cool stuff. What's the index? What letter do we use to keep track that changes? I, which means anything without an I is just a constant. I really want to stress that. If it doesn't have an I in it, it's never going to change. Now, there's some benefit here. Decision time, and whatever you guys want to do, maybe. Do we distribute these or no? Enthusiastically, yes, we should distribute this. Good. So let's do that. This is the sum from I equals 1 to n of 300i over n squared. And I'm going to write this a little bit differently. Why would I write it like this? Because this looks very, I've changed form. Is it because I'm neurotic and I want to write this a very specific way? Or is there a reason that I've rewritten it this way? What's the reason? So I'll rewrite the other part of it the same. This is just 300 over n squared. Okay, the question at hand right now is, Rafa, you're right. I did have a reason to rewrite it instead of like, just to show you what I mean. It's a very subtle change. All I've done is I've written it differently than that. Why? Factor out, what do you mean? Yeah, what doesn't change? So careful, you're backward. I'll rephrase the question, don't change your answer. What's the only thing that we let change? I. N is a what right now? It's a constant. When I write it like this, there's a couple awesome things that shake out. We've maybe used this language, I'm not sure, but you're going to recognize it. I have the summation of a difference. What's the second half of that statement? The sum of a difference everybody's whispering it, you're going to be right, is the difference of the sums. Now, I don't think we've used that language this year with summations. Where have we used this? The limit of a sum is the sum of the limits. The limit of a difference is the difference in limits. The derivative of a sum is the sum of the derivatives in most cases. Like we've used this over and over. We're just switching it. So we're going to clean this up. What's better than a single sum with two unmatching things? And rather, rewording that, how can I rewrite this? Using this lovely statement. There's two summations, right? If I look at this and it's almost like I'm distributing, what's the constant multiple that's going to come out in front of this one? So we get 300 over n squared times the sum from I equals 1 to n of what's the only thing left inside? So careful. We can do I minus 1. I'm cool with that. I'm actually way cool with that. I minus 1. Not what I was expecting to hear, but that's a good call. It should have been what I was expecting. You saw something that I didn't, which is good. Do I still have the sum of a difference here? So if we go one more step, and I might have talked a little bit too much with the complement stuff. How do I write this as two sums? It's the sum from I equals 1 to n of what's the first argument? I minus the sum from I equals 1 to n of what? 1. Okay, here's the deal. I want you guys to use the summation rules that we had at the start or a few minutes ago. There's going to be a few missing lines. I want you to get to what this equals as nice as it does when you multiply it. Once you have a value here, whatever this is, this evening your job is going to be to take this, and then you're going to take the limit as n approaches infinity of whatever's in here. One problem to finish tonight. Maybe tomorrow we'll cross out something and change it in our notes from today, but I'll see you cool cats then. If you need help with this, can you come in at lunchtime and do calc with me? Yes, and we could also do an inductive proof. Don't forget, I got you. Later, Raiders.